the day, and it looks like I have like most people. There were 60 people made choices, and I think my class isn't that much bigger than that. But I will say, I will give you a grace period until tonight at midnight. If you did not do one of those topic choices to get that done, tomorrow morning I'm going to finalize that, and I won't be taking any more. That'll be over. So if you don't get it done by tonight, that is a zero. Does everybody know what I'm talking about? I hope so. Um, I really do. Like I have 60 people who already did it, so I don't even know if I don't have anybody who needs to get it done. But the reason I want you guys to get it done right now, if you have it, is because the next step is due this Friday, and the whole point of this is for you to spend time thoughtfully engaging with the material. And if you do it all in one day, I do not believe you have thoughtfully engaged. So this week, um, if you look on week 9, you'll see the explain something topic. It's due on Friday, so you need 200 to 250 words. So this isn't like a big thing. This is just like one page. You need to have the topic that you chose on there. You need to explain what that topic is. You need to tell me what analogy or example from your own experience or technological application that you're using to explain this concept, and you need to tell me like how that analogy works. So for example, if I were going to talk about um, electricity flowing around a circuit like water falling down a hill, I might say the water goes from high to low, like the electric current goes from the positive to the negative side of the battery. And that the resistors would act like blockages in the path where the water would try to find the easiest path, the path of least resistance down the hill. Just like electric current tries to find the path of least resistance through the circuit. Um, does that make sense? Okay. Um, I should note, so I'm using Turnitin to do these just like I did last semester, where I allow up to about 20 words in quotations. If you want to quote from some source, that's fine. If you copy your entire thing from Wikipedia, you'll get a zero. And if you do want to use any quotations or sources, please do cite them. I don't have a preferred format. Just make sure if I need to find where you got this information from, I can. Okay. Does anybody want to ask any questions about this or the projects in general? You guys feel confident? Okay. Okay. So your chapter 11 is we'll see how far we get. We'll see how far we get. Um, so you do have a quiz over the weekend over whatever we're going to hit. Uh, Definitely be working on your chapter 11 homework. 30 seconds. And I feel I can probably get through this. I feel I can probably get through this in this week. Yeah. Okay. Yeah, I feel good about this. I can get through chapter 11 by the end of this week. So yeah. Chapter 11 homework due this Friday. Okay. Okay, I think that's everything. Does anybody have any questions before we actually like start the class? All right. So I did want to start off with this demo that I wasn't sure how best to display this. I usually have an overhead, but what I have right now is a camera precariously perched on my laptop. So I should probably go to like speaker view, so I'm big, and maybe, what's the best way to do this, guys?
3 dots. Is there
Add pin. Oh, hey, look at that. Okay, so you see inside my box, so I have basically just a magnet. It's got a north side, it's got a south side. It's not a super strong magnet, but it's got enough of a magnetic field that when I pour these iron filings on top of it, it is going to pick up the magnetic field. Now, I want you to note that it doesn't move the iron filings. So like you see, they're not accelerating from one spot to another, right? They're not scooching across the page, but what they're doing is they're rotating. So they're aligning their north and south to go with this magnet, where the north side of the north side of the filings port towards the south side of the magnet, and vice versa. And you can kind of notice here. Let me add a little bit more here. Wow, that magnet's better than I thought it was. Maybe you'll notice. So look around the edges, and if I shake this, will you be able to see it? Do you see that the field starts to look stronger? Because what's happening here is it's being able to twist more. And again, it's not like the stuff over here is moving towards or away from the magnet. It's just aligning more with the magnetic field. And so what I want you to think about with this is I want you to think about how this magnetic force that is pushing on this filings is not causing it to go in a line. It's causing it to twist in a circle. Sound reasonable enough? Okay, I'm going to leave this over here if anybody wants to play with that in class. Okay. So that's I tried to draw a picture of a magnetic field last week. That's what a magnetic field actually looks like. I hope it's illuminating. And so let's get back to what we were doing. Do you guys remember where I left off? Did I leave off somewhere specific? Yes, no, maybe. Okay, good. Did we do cross products? Okay. Okay. All right, let's do some cross products then, because that's actually a really good lead in to cross products. Where, here we go. I don't need it anymore. Where, start screen. We have this equation for force that's QV cross V. Okay, so the Lorentz or magnetic force, QV cross V. Okay, and so we looked at the units, and I think I talked about how the velocity needs to be perpendicular to the magnetic field. But let's talk about that some more. So what a cross product does is it takes what's perpendicular between two vectors and multiplies those things. Takes what is perpendicular between two vectors and multiplies. Okay. Multiplies. So if I have two vectors, just two random vectors, A and B here, and I want to take the portion of A that is perpendicular to B, I will drop a perpendicular down from A onto B. Sound okay? And if I'm looking for that perpendicular portion, is that going to be an A sine of theta or an A cosine of theta? This is the perpendicular portion. Given theta is the angle between the two vectors, do I want A cosine of theta or do I want A sine of theta? Sine. Exactly right. So that A cross B is just A sine of theta times B. And of course, we could do the opposite of this as well. If instead of the perpendicular portion of A to B, I wanted the perpendicular portion, perpendicular portion of B to A, I would drop a perpendicular down along A. And again, if I'm looking for that perpendicular portion, am I looking for B sine of theta or B cosine of theta? Still sine, which is really good because if I want, because the equation shouldn't change. The perpendicular portion should always be the sine. It shouldn't switch back and forth between sine and cosine. So that if we want to say that, if we want to find this force, we can write this as QVB sine of the angle between V and B. Okay, and we're gonna put magnitudes around all of that, absolute values around all of that. Okay, so first off, is everyone kind of happy with this perpendicular business? We haven't quite got to why it matters, but do you believe that this is a good equation to take the perpendicular portions of V and B and multiply them? Okay, because then we need to talk about these absolute values, because I started throwing absolute values everywhere. Because the truth is, A cross B is not the same thing as B cross A, because one of them is going to have a minus sign. And that's where the right-hand rule comes in. Where if I want to take the cross product of two vectors, a cross product is also sometimes called a vector product because it takes two vectors and gives you a vector back, as opposed to like a dot product, which takes two vectors and gives you a scalar back. So to determine the direction that you'll get, you use the right-hand rule, where if I have two vectors, A and B, A cross B, just the direction of A cross B, you take your right hand, you put the hand bones in your right hand along the direction of A. So let's agree on directions. That way is X, that way is Y, that way is Z. Sound okay? So my A is that way. Whoosh, that way. My B points mainly towards the ceiling. So A cross B. A cross B. Sorry. Too many surfaces here. Hand bones along A, and then curl your fingers in the direction of B and point your thumbs. Your thumb should be pointing towards the back of the room. Is that what you guys are getting? You can also, I see a few of these, and that's also a really good way to do this, where if you want to do your pointer being A, second finger index being B, thumb being the answer, that works as well. Okay, are we all getting towards the back of the room here? In terms of the coordinates that I wrote up there, X, Y, and Z, which way would that way give you? Is that an X, Y, or a Z? According to what I have up here, and I'm really sorry, I'm going like back and forth. According to what I have on the screen, that's X, that's Y, that's Z. So Z, okay. So this, whatever answer, it's in the positive Z direction. Okay, let's do this again, but let's do B cross A. Now B cross A will give us the same magnitude, so I can still say that's C. So like A sine of theta B times B equals the same thing as B sine of theta times A. But what direction is this going to be in? And so the big difference here is now instead of putting your hand bones along A and curling towards B, put your hand bones, yeah, there you go, along B and curl towards A. So your hand should be that way, your fingers then point towards A and your thumb points towards the front of the room. You can also, doing it this way, this guy goes along B, this guy goes along A, thumb towards the front of the room. Okay. And so front of the room, what direction is that going to be in terms of X, Y, and Z? We're still on the Z axis, but is it the positive Z axis or the negative Z axis? Excellent. Negative Z. Okay, I like this. This is pretty good. There's also a few shorthands that you're probably going to see. So if you see a circle with a dot in the center, that means out of the board. So like pointing out of whatever surface you write that on. If you see a circle with an X in it, that's shorthand for into the board. So like into whatever surface you're writing that on. But generally you can just have like Z and negative Z, and that'll do the same thing. Although you should always write down your coordinate system. Now, let's do a few more of these. And in particular, let us look, catch up little program. Let us look at your homework, because half of the problems this week are right-hand rule problems. So, that's right. Okay, so if I was looking at number 4, oh, that one's a hard one. Let's do that second. That one's a really hard one. not a really hard one, but there we go, that's better. If I'm looking at number 13, just to start off with. Number 13 gives us a magnetic field that's into the board. So if you so you're going to see like the circle with dot and x's. X's are going to mean this field is into the board. And I'm going to have a positive charge going that way. And let me give our, so there's my X, the Y, and the Z. So my B field is in the negative Z direction. My velocity is in the positive X direction. And I would like to figure out the direction of the force that this guy is going to see. So to figure out the direction of the force, I need to do a B cross B. So yeah, right hand pointer goes in the direction of the velocity, so just like lay it on the page. Then you have to, I like what you're doing, spin your hand so that this guy is going to go in the direction of these X's into the board. And I see lots of thumbs pointing towards the ceiling at this point. This way, so this finger point it along V, then take this guy, and now you spin your hand. So keep this guy in the same direction, but spin it so this finger goes into the board. And now you notice your thumb's going up, right? And yeah, so the hard part is making sure that you keep the first finger's orientation. So like you don't go like this. You hold that straight, and then you can rotate. And then you rotate so you get that second finger in the right spot. And you notice that if you used your left hand, you'd get the exact opposite answer. So we're using a right-handed system, and what people mean when they do a right-handed system is that this gives you the same answer versus this. Oh, that is such a good question. Remind me to come back to that question in a second. So for this first one here, the force will be in the Y direction. Let me ask you a question though. What if instead of a positive charge, I had a negative charge? And so everything else was the same, but instead of a positive charge, I had a negative charge. Looking at this equation, does the direction of my velocity change? No, okay. Direction of my magnetic field? No, okay, so this is still going to give us a plus Y. What about the sign of this charge? It's going to become a negative, so now I have a negative Y. So which way is the force going to be in? Down, perfect. So for this one, same magnitude of force, but in the opposite direction. So if you have a negative particle, you do the same right-hand rule, you just flip your answer. Is that okay? Shall we do a few more of these?
Just to be clear, the pointer is only V.
Yeah, so V, force. And you can go backwards and forwards on that, and we'll talk about that in a second. But really quick, William wants to know where to submit the explain something topics. If you go to this week, go to week 9. On the iLearn, you should see an explain something topic assignment. That's where you do it. Sound okay? And let me know if there's anything weird about it, because I think I have it set up right, but I haven't like double checked everything. So if there's something weird about it, just let me know. But meanwhile, let's,
He asked to do more.
oh, when, Friday, this Friday at midnight. Okay, this Friday at midnight. Okay, okay. Once again, let's look at some various. Let's do a few more right-hand rules. So for number 15, and for part A, we have a magnetic field coming out of the board. X, Y, Z. And I have a positively charged particle moving towards the bottom of the board. And let me caution you about using words like up and down for these problems, because there are kind of two ups and downs where you could think of out of the board as up, or you could think of the top of the screen as up. So X, Y, and Z are really good ways to think about that in case you end up getting confused. Okay, but anyway, so I have a magnetic field out of the board. I got a particle going towards the bottom of the screen. I like this answer over here. What are we seeing in the x direction? So yeah, so I have V going down. I have V coming out of the board, and your thumb should be pointing towards that side of the room. All right, so I have a force this way. So I have a velocity in the negative y direction cross a B field in the positive z direction, giving a force in the positive x direction. All right. This next one might be easier. So here I have a magnetic field in the x direction, and I have a positive charge moving in the y direction. So what is the direction of the force for this? You got it. Yeah. Yeah, you got it. So are we getting in the negative z direction, right? All right. Force negative z. Okay, one more of these, and I'll talk about a pattern. Last one on this one, we have a magnetic field into the board. So B's in the negative z direction, and my velocity is in the x direction. And this is, again, is a positive charge, as a positive charge. Okay, what do we get? B cross B. Good, good, good. Excellent. Positive y. Okay. All right. This is excellent. I do kind of want to note a pattern. I don't know if you've noticed it, because it's not. We've done a kind of wide range of things here. But what you should notice is if we cross the x direction with the y direction, you get the z direction. So plus y plus x plus cross plus y equals plus z. And if you cross the y with the z, you get the x. So if you cross y with the z, you get x. And if you cross z with x, you get y. So z cross x gives you y. And I'm kind of hoping you see that I'm doing a cycle here, right? X, if I do x cross y, I get z. Y cross Z, I get X. Z cross X, I get Y. And if I go backwards, if I do Y cross X, I get negative Z. So if I flip these, I get the opposite. If I do Z cross Y, I get negative X. And if I do X cross Z, I get negative Y. And so again, this is kind of that right-handed system where you know your system is right-handed is it if you can draw this X, Y, Z and do X cross Y and get Z. If you flip that, you X cross Y, you get negative Z in the opposite direction. Okay. Okay, it's a good cycle. Okay, there's only one more right-hand rule problem I want to look at because it's the difficult one. And it is number 5. Okay, so number 5 is difficult because instead of giving you the velocity and magnetic field, it gives you the magnetic field and the magnetic force. So I have a B coming out of the board, and I'm going to have a magnetic force in the positive Y direction going to the top of the board. So I have some particle, it's moving in some direction, but the force is going towards the top of the board. What direction is that particle moving? What do you think? Okay, so yeah, so I'm gonna need to curl, this finger is gonna need to go out that way, right? This thumb needs to go whoosh towards the ceiling. And so the only way to keep this guy towards the back of the room, that guy towards the top of the room, is to point this guy like right towards the negative X direction. Sound okay? I'm having a lot of trouble. My screen is mirrored from you. Yeah, no, I think. Okay, negative X. I'm sorry, I have to do it up here. So if I'm this way, yeah, it works. Okay, sorry. Whew. Okay, that sound good? Okay. Let's do another one of those. Okay, so for this one, my magnetic field is in the positive X direction. And my positive charge is got a force towards the top of the page. So which way is it moving? I like the Z. Yeah, so the only way to get my thumb towards the ceiling and my index towards the positive X side of the room is for my pointer to go to the back of the room. Is that what you guys are seeing? Okay, so here the velocity is in the positive Z direction, or this thing's like coming out of the board at us. Okay, okay. That was a whole lot of right-hand ruling. Is everyone kind of okay with this concept? Okay, the rest of this chapter is about, the rest of the semester really is about right-hand rules. So if you're not, tell me now. It'll save you so much heartbreak. Okay. Actually, let me ask you just one more of these. Let's take any one more of these. What if I had a force? What if I had a magnetic field going this way, and I had a particle going that way? Tell me about the magnetic force on this guy. And also tell me that this problem doesn't make sense. The problem doesn't make sense because I'm asking you to take a cross product, which is multiplying the parts of these two vectors that are perpendicular, of two parallel vectors. So the answer is 0. And so this is, so there, the force here is 0. And this is actually going to be kind of a big thing, because what you can have a charged particle in a magnetic field and get 0 force. One way to do that is to have the velocity be 0. So if your charged particle is just at rest in that magnetic field, no force. Kind of like those iron filings. I put them right next to a magnet, but they didn't like speed away. They just stayed put. The next thing is that if your velocity is parallel to the magnetic field, there's not going to be a force. And so this is kind of going to be a thing where we don't see magnetic forces push things in lines. They don't go in lines. What they're going to do is they're going to go in circles. Because if you remember from 220, when we started talking about cross products in 220, was when we needed to talk about torque. Where torque was again a cross product between a length and a force. And we always wanted to take the perpendicular part of that force to the length, right? We had some length, and if we wanted to twist it, we pushed it perpendicular. Since this magnetic force is a perpendicular force from the get-go, like all it can do is push in a perpendicular direction, it's not going to cause things to go in line, it's going to cause things to go in circles. Sound okay? Okay. Excellent. Whew. If that's okay, let's talk about how that can look like. Because we're gonna look at a cyclotron frequency first. One of the most classic things to do with these forces is to make a cyclotron. I'm going to call it a cyclotron frequency, but we'll look at this. Where let's say I have a magnetic field that goes into the board. Okay. So I have this magnetic field. It's in the negative z direction. I have an x, I've got a y, and I've got a z. And I'm going to put a positively charged particle right there. And I will give it an initial velocity in the y direction. It's going to experience a magnetic force in the F equals QV cross V direction. Which way will this force point? In the negative x. Everyone happy with negative x? Okay. So it will experience a force in the negative x direction. I should have color coded that blue. Looking at that, that means that this particle is going to accelerate in the negative x direction. So it's going to curve around to right there, where now it'll still have its velocity in the y direction, but it's also going to have a velocity in the x direction as well. So now its velocity looks like that. Okay, go ahead and do your right-hand rule again and tell me which way the force is pointed. So now my velocity is this way, right? My fingers point into the board. And now my thumb doesn't point like in the negative x, it points kind of down and in the negative x, right? So now my force looks like that. Okay, that means my particle is going to bend around some more till it reaches right there, and its velocity will be totally in the negative x direction. Which way will the which way will the magnetic force be in now? Like that, down. Are we starting to see a pattern? Yeah, the force is always perpendicular to the velocity, which makes sense because that's what a cross product does. It takes two vectors and gives you a third direction that's perpendicular to the first two. That's the whole thing with a hand, that each of these fingers is perpendicular to the next one. So no matter which direction the first two fingers in, your thumb's always perpendicular. We're going to do two more. If I'm right here and I'm going in the negative y direction, which way is my force? In? No, take your time. No. Oh, no, you're right. Sorry. I'm mirrored. Excellent. Yes, your force is going this way. And I'm hoping you're seeing the circle that we're going in now, right? Because this is a circle. And so if we're at the bottom of the circle with our velocity in the positive x direction, we should see a force in the positive y. So, this is what I was talking about when I was saying that magnetic forces don't push things in line. They point things in circles. So they cause things to spin. And so what I'd like to do with this thing is I would like to solve for the radius of this circle. Probably also solve for the time it takes to get around that circle. So I want to solve for the radius. I want to solve for the period. And I don't know if you guys remember from mechanics where the period is how long it takes to get around once. So it's a time. We're also going to solve for an angular velocity. So like how many times it can get around a circle per second, basically. Notice that's also a frequency. What sort of thing? So looking at this, I'm clearly going to need some known. So like I'm getting this equation for radius, but what it will be in terms of? I should have a magnetic field, because if I don't have a magnetic field, it's not going in a circle in the first place. I'm going to need a speed, because the bigger the speed, the bigger the force. And again, if I don't have this velocity in here, I'm not going to have a circle at all. There's one more thing that's not on my screen right now, but if you think about trying to make something go in a circle, what might make it more difficult to push something in a circle? So I'm gonna go get in a vehicle and I'm gonna drive it in a circle. Should I use my like little electric leaf, or should I use a city bus? Which one can I get to go in a circle better? Do you guys know what a leaf is? Is that like, okay, so it was like one of the first electric cars. It's like this tiny little car. Right. So large things have more mass means more inertia means it's harder to get it to go around a curve. So I'm also going to need to know whatever this particle's mass is. And so we'll do, like we'll say I have an electron or I have a proton or something, and that will give me that unknown. Where it seems to me that you guys are saying that the higher the mass, the bigger the radius, because it's harder to get things to go in a circle if they have bigger mass. Okay, so we expect for bigger mass, bigger radiuses. What about the magnetic field? If I have a higher magnetic field, what do you expect to happen to the radius? And this might be a good time to look at a limiting case. What if my magnetic field is just like super weak, really small? Do you expect this particle to be affected by it a lot? No, okay, so if a particle is not affected by a lot, we'd expect a really big radius. So when my magnetic field goes down, my radius goes up. Can we say the opposite? If I have a really huge magnetic field, would you expect it to affect this particle more? All right, I like it, I saw a nod. So if I have a larger magnetic field, I expect a smaller radius. And the same thing with my speed, right? Because my force depends on my speed. The faster I'm going, the smaller this radius is. So when I'm doing my equation, I expect to get radius equals to something with the mass on the top and the magnetic field and the speed on the bottom. Sound okay? I should add at this point that I'm going to not put that perpendicular in until the very end, but I could have a velocity that is three-dimensional, where it's not just going around in this xy plane, but it's also has a z component as well. But as we just saw, that any component of the velocity that's in the same direction as magnetic field, it's not going to affect my magnetic force. So we'll talk about the z component in a second, but know that when we're looking at this speed here, the velocity here, I only want the part of the velocity that's perpendicular to the magnetic field. Okie dokie. This looks great. Let's solve for that r. The way we're going to solve for that r is we're going to draw a free body diagram and write down Newton's second laws. I am going to go ahead and just use this spot right there. Since this whole circle is symmetric, you could pick whatever spot you wanted. That would be fine, but this one's a nice spot. From that spot, we have the magnetic force. This is a trick question, but are there any other forces we should be looking at? If this wasn't a trick question, what sort of forces would you be like, well, maybe we should think about gravity? Solid answer, right? And I do want to kind of remind you of what we were talking about like way back in the beginning of the semester, where we had a lot of problems with electric force. And we said, you know what, we're just going to ignore gravity because it's so small compared to the electric force. Same thing here. We're going to ignore gravity because it's so small compared to the magnetic force. Also, we're going to ignore air resistance because probably this is happening in a metal anyway. But that's really just not a huge thing compared to everything else that's going on. Okay. So I have my force that I care about. Do I have an acceleration? Yeah. Centripetal acceleration, right? For this particular spot, the yellow box, which way is the centripetal acceleration going to point? in general, where do centripetal accelerations point? Towards the center. Perfect. No, towards the center. That's exactly the right answer. You guys are doing great. Okay. Doing great, guys. The centripetal acceleration points towards the center of the circle. And I won't even like rake you over the coals on this one. It's equal to the speed squared over the radius. Okay, so since everything's pointed in one direction, I'm going to go ahead and call that the positive direction. I have my magnetic force, and I have my mass times acceleration. For my magnetic force, at this point, I'm just going to say QVB. And the reason I can say that is that I've already pulled out the perpendicular component of my velocity, right? So I've already said that this is the perpendicular part of that vector. So that sign doesn't matter. QVB, because this is the perpendicular speed, just like this is the perpendicular speed. I don't need to worry about the sign at this point because since I've already put all my directions in, I don't need to include more signage or right-hand rules. And so I have QVB equals mv squared over r. And I was solving for r. So I'm going to put r up here and everything else over here. I'm kind of hoping that you guys see that one of these speeds is going to cancel out like that. And so I'm gonna end up with something that we call a cyclotron radius. Where r equals m v perp over qb. And notice that this very much matches what we were. Did I get that right? Yeah, I did. This very much matches what we were talking about, where the bigger the magnetic field, the smaller the radius. The bigger the mass, the larger the radius. The only thing it kind of breaks up is this speed. And that's actually a pretty interesting thing because we said, well, shouldn't we, as we're going faster, have a larger magnetic field? And the only place that really broke down was when you noticed our centripetal acceleration also depends on speed. So we had some momentum there that we had to shift as well. Okay, everything else though looks pretty good. What sort of units would you expect to get if you calculated a cyclotron radius? Meters, yeah, so do keep in mind, this is a length. Okay, cool. Let's derive a few more equations and then let's talk about why we care about this. So we have this radius. We also wanted the period and angular velocity. Well, let's start with the angular velocity, where I don't know if you remember from last semester, where we could connect linear velocity with angular velocity through this radius, where if something was going in a circle, how fast it was moving was related to what sort of angle it went through with respect to the radius. So the further out on that circle, the linearly faster you'd have to go to cover the same angle. And so that's this equation, where if we wanted to talk about this angular velocity, or in some cases you could call it an angular frequency, we'd have the v perp over r. Well, let's look at this. So this is V perp, and R is mv perp over qb. M V perp over QB. I'm hoping everyone sees that this V perp goes away and the QB is going to come on top. QB over M. Okay, so this is the, generally we just call it the cyclotron frequency. Because the next thing we're going to do is we're going to say, well, the period is 2 pi over that omega. Do you guys remember that part from last semester? Okay, I'll leave it then. And once you plug in QB over M, you end up with 2 pi M over QB. Okay, and that's just the period. I don't think we call that anything. Okay, why do you care about this? Why you care about this is we're about to do just several weeks of charges moving in magnetic fields. They're always going to go in circles. And so this thing gets called the cyclotron radius and cyclotron frequency because one of the first applications people used this was for cyclotrons, which is kind of a small particle accelerator. Do you guys, particle accelerators, is that still like in the common consciousness, or it was a big thing like 5 years ago? But you guys were too young for the Higgs boson, I guess. It was the thing, you know? So generally particle accelerators are these giant underground things where they're like a mile in diameter. So like huge, where you send particles around in this giant circle and run them into each other. A cyclotron was like one of the forebearers of this, and it would fit nicely into like a basement room. Still would take up the room, but you could, it was this kind of circle instead of like a diameter of a mile circle. So a lot of the math that went into, I have particles moving in a magnetic field, they just called it like the cyclotron frequency or the cyclotron radius instead of charged particle in a magnetic field radius. Okay. And since we're about to do just a ton of stuff with particles in charged particles in magnetic fields, all our equations are going to look a whole lot like this one. So this one's just going to come back again and again. And if you're ever trying to figure out, hey, this is going in a circle, but like, how is it moving in a circle? That's probably where you want to be. Okay. So far, so good. All right. Let's talk about helixes. Because, only for a little bit. And I think you guys get to see this in lab this semester. So like, be really happy about that. It's very cool. Say I have a region of space where I have this magnetic field in it. And then I put my charged particle in it, so it's going like this, where I have a portion of the velocity that's perpendicular to the field and a portion of the velocity that's parallel to the field. Now, as you guys have thoroughly seen at this point, the portion of the velocity that's perpendicular to the field is going to cause this thing to go in a circle. But there won't be any force that will change the velocity in the parallel direction. So for example, if there wasn't that parallel speed, it would just go in a circle like that. But since there's no force in that direction, it'll just keep moving in that direction at a constant speed. which means if I'm going in a circle and moving forward, I'm doing this. Where at each spot in this, I have some forward velocity, and I also have some velocity that is perpendicular. Whoosh. I'm going like this, so like, man, I'm having trouble drawing this. Portion that's parallel, portion that's perpendicular, like that. That looks better. And that's what's going to cause, and that's where this helix is coming from, where the radius, so if I take one of these circles, the radius is that mv perp over qb. And the parallel component is just untouched. You want to put the parallel velocity in here, and you want to even put the total velocity, right? Like there's some total velocity here where the perpendicular would be like v sine of theta of that. It's really only the perpendicular component that matters. What did it, this was no, I think I'm good here. Okay, kind of makes sense. One or two, have one more equation I want to pull out of that, and that is the kinetic energy of something in this system, where you might want to talk about energy considerations. And certainly we're going to talk about like potential energy of magnetic fields. And so you might want to have a kinetic energy to go with that, where I have 1/2 m. I'll put in my v perp here. But of course I have to say, well, R equals m v perp over qb. In my notes, I just assumed I could do this math in my head. That was silly of me. R qb over m. Yep, I got that right. Okay. So R qb over m. And that's squared. And so let's see what I'll have: an R squared, a Q squared, a B squared. I'll have an M squared on the denominator, but I'm multiplying by an M in the numerator. So I'll just have one factor of M in the bottom. And I'll have a 2. Excellent, excellent. Okay. And I think that, yeah, that looks good. So this is the kinetic energy of a charged particle moving in a B field. Okay. Any questions about that? It's a lot more equations than thought there, but does it kind of make sense? All right. I don't think I have a huge amount of time left, but let me kind of prep what we're doing on Thursday, and that is we're going to look at mass spectrometers and velocity selectors. Spectrometers and velocity selectors. Which, have you guys ever heard of a mass spectrometer? Maybe in a crime show? Or in, oh, sweet. What lab do you work in? Excellent. And what did you use a mass spectrometer for? You didn't?
I remember setting it up, and I remember a few complicated stuff, like prepare it, but.
Right, yeah. Did you put like a sample in and hit a button and then it? It totally, yeah, it'll do that. And then it'll tell you like what's in the sample.
Yeah, like what depending on the light that you like.
Excellent, excellent. Yes, that's a mass, I like that. That's a mass spectrometer where it can look at a particle and it can move it in a magnetic field. And depending on the mass of that particle, it can tell you what type of particle it is. So for example, if you have a electron and a proton, same charge, you can shoot them into a magnetic field with the same velocity. But the electron being much smaller will make a really tight circle, and the proton will make a much larger circle. These are really nice because, like, if you have helium, helium is the same here in lab as it is in the sun or at some planet in some faraway galaxy. And so just by looking at the frequency of the light coming off of it, you can say, hey, that I'm looking at this faraway planet, it's got this specific light spectrum. I know what it's made out of. And that's really, really nice because we're never going to go to some of those planets, probably. So next time we talk, we're going to talk about mass spectrometers and velocity selectors, both of which use this idea that charged particles go in circles, and you can use them to make machines like mass spectrometers. Particle beams, really, very cool. Okay, any questions? Yes.
You got good question to the inside.
Okay, then don't forget to get those. If you haven't chosen a topic, then that project choice thing, do it by tonight because I'm finalizing that tonight. Yes.
Maybe the topic is not, it's just kind of like a draft of what you say you did, or is that?
So this is just like the outline where you're going to just write a page about your concept, your analogy, and how it works. Okay, awesome. Okay, I'll see you on Thursday. Have a great week. Online people, are you good?
Yeah, I'm good.